Yaakoub Kharma at TACC and Matt McKenzie at NICS have been working with the Ronald Levy at Rutgers, I believe, in using the Saga framework for parallel molecular simulations and splitting these across multiple sites, I believe. Saga is going to have a more prominent role in XSEDE than previously, so I think it's going to be interesting for us as extended collaborative supporters to hear more about this technology and how we might apply it to other projects as they come in. So with that, I'll let you take it.
All right, so good morning and good afternoon to those of you who are on a reasonable time zone. My name is Yaakoub Kharma. I'm here with Matt McKenzie, and we'll be talking about the ECSS project called Distributed and Loosely Coupled Parallel Molecular Simulations using the Saga API. What we're going to be talking about today is a bit of the background information and the progress we've made since we started September 15th. Real quick, an outline of what we're going to cover today. There's a fair bit of material. We will be going a bit fast, and there will be a Q&A session at the end, and obviously feel free to contact us directly with any questions that you may have. The purpose of this ECSS is to prepare the Saga infrastructure necessary to run large-scale distributed, coupled, and uncoupled replica exchange molecular dynamic simulations with impact and AMBER codes. This effort is supported by the NSF and the NIH grants. The main science problem, for those of you who are interested, is the protein-ligand binding energy calculation. In this simulation, replicas exchange lambda values according to a particular probabilistic prescription. The idea is that you have multiple parallel simulations that need to communicate in a non-uniform asynchronous fashion. And this presents unique challenges, making it an interesting problem. Obviously, it's not just interesting from a purely computer science perspective. The scientific effort is also a funded CDI Type 2 project with Ronald Levy as PI. The ECSS was requested to support the infrastructure to do the science and work, and essentially we got dedicated support and a member of the Saga team to help us throughout the entire project. As we said earlier, it's interesting, it's challenging, and we will be running into a few problems. One of them is obviously we will be running thousands of replicas, each a somewhat large simulation in its own right, 32 to 256 core simulations. The infrastructure will need to be able to launch, monitor, and manage these simulations when they are independent, when they are loosely coupled. It will also need to be able to checkpoint and restart replicas because they will be running from hours to sometimes weeks. So we will also need to be able to communicate the asynchronous data in case they were coupled. At the moment, this is a file-based data exchange, so one simulation dumps a file, another simulation reads it. This obviously can take a whole lot of synchronization effort. And as consultants, we will be faced with software integration and testing challenges. We will be facing high I/O load, file clutter from various simulations, Globus issues, as is always the case, environment issues, particularly when we're launching on the back end, MPI run and MPI host file issues, runaway job issues, jobs that continuously launch because of a bug or an infinite iteration, and we have to kill them manually, and versioning numbers, well, package version issues because we have to sync the version numbers of packages across multiple sites. The solution that we came up with is essentially Saga, the simple API for grid applications. It is a stable and uniform community-based API that has a restricted scope. In particular, it builds on the underlying grid or grid-like services, so Globus Unicore, G-Lite, Eucalyptus, Amazon EC2, Condor, what have you, and provides adapters to move files, launch jobs, and so on. The infrastructure building blocks will run on XSEDE, National Grid Service, European AGI, or the cloud service providers. So it's very portable, and it allows us to run on a wide variety of hardware underneath. It's also an OGF standard and an official access layer to NSF XSEDE. Saga has been around for a while. It has been deployed on TerraGrid and as a CSA. It is production-grade software, but it hasn't been tested on the large scale that we want to test it. Well, we want to run it on. We need to obviously perform a lot of sanity checks. Perpetual demos are constantly running. They monitor performance, and they continuously find problems that the Saga team identifies and fixes. And what we're working on is hardening and resolving issues while running at large scale. On the TeraGrid, Saga has been deployed as a CSA on Ranger, Kraken, Lone Star, and Queen Bee. The advert service, a particular service running as part of the Saga framework, used to run on a small machine hosted by the Saga team. The replica exchange workflows, ensemble common filter workflows, and couple simulation workflows were developed early on. They were used as proof of concept, running 128 ensemble members, for example, in the ENKF workflow case. Small, limited, not so terribly large replica exchange simulations. And there was a basic science gateway framework that obviously got improved as the years went on. Oops. On XSEDE, essentially, we have deployed the latest and greatest Saga, version 1.6.1, on Ranger, Kraken, Lone Star, and we are setting up on Blacklight and Trestles. We have automatic user deployment and bootstrapping scripts and virtual images for the Azure service and science gateways that users can roll on data query. The major push right now is to make the infrastructure system-friendly, production-ready, and user-accessible. This is a screen capture of one of the Saga demos. This is a perpetual demo running on XSEDE. In this case, Blacklight, Kraken, Lone Star, Ranger, and Trestles. It also runs on FutureGrid and the OGF GIN. Saga is made of three major parts, three major supporting pieces. The advert service, we have touched on this earlier, it's essentially a central data exchange for distributed coordination. There's also the BigJob framework, which is a pilot job framework that submits container jobs that run small jobs underneath. These small jobs can be parallel, that is, they can run multiple cores, they can be distributed across multiple sites simultaneously. And the third component, the third supporting infrastructure, is the DARE Science Gateway that supports BigJobs and allows you to submit BigJobs that are distributed across XSEDE. Oh. There we go. Oh, right. Sorry. BigJob, the Saga implementation of a pilot job, differs from other pilot jobs or job launchers that we would have on certain machines. For example, Ranger, we have the launcher module. It differs in that it supports parallel jobs and it can run distributed across resources. So this reduces the total time to completion by reducing queue wait time. Furthermore, because of its simple architecture of job manager, pilot agent, and advert service for communication, it's easy to set up distributed workflows. You can have anything from a dynamic ensemble common filter with a fault tolerance and sensor data input workflow to a pipeline workflow, what have you. And it insulates the application from the underlying hardware. So in our ECSS, the replicas can be running through Gram submission, Condor G, Unicore, Nimbus, EC2, Eucalyptus, what have you. Obviously, there's a whole lot of users currently using BigJob. We are supporting a few of them as separate projects, and because we support Saga as users and developers, and work closely with the Saga team, so we have to handle their tickets either way. Right now, I'm going to hand off to Matt McKenzie, who's going to talk about one particular such case, the BigJob effort of Tom Bishop. Matt?
Yes, thank you, Yaakoub, and good day, everyone. This is a BigJob effort from Thomas Bishop. He did computational studies of nucleosome positioning and stability. And a quick background of his science. As DNA is wrapped from the double helix strand into the histones, making the nucleosomes, and that compacts even more into a chromatin fiber and then into a chromosome, he's interested in how the DNA actually wraps around the histone, as seen in this picture. And basically, this is a high throughput of high performance computing on how you create this nucleosome. If you can think about the histone as a ball and a pulley around a string, the string being the DNA strand, this problem space of how it wraps around the histone is very large. The simulation itself is pretty large itself, being 160,000 atoms. We used here NAMD 2.7 with the amber force fields. As the simulation progresses, it's actually multiple nucleosomes with the sequence of DNA, there's 21 different base pairs on the histone. So as the DNA is wrapping around it, it's sliced in another way where as soon as you take you add one DNA base pair to the histone strand, you remove one. We'll have the actual animations on our website. Nancy, I'm sure, will provide them, as you can see how these are created. But overall, to understand this problem, there's a lot of simulations involved, nearly 7,000, to see how the DNA is wrapped around the histone. Here are their starting positions of the 16 different nucleosomes. And I can't show an animation here, but as you can see, the core of the histone protein, the DNA wrapped around it. And then now Tom's team ran this on Ranger, Lone Star, and Kraken. At first, they looked at various sub-jobs here. These would be 1 nanosecond of each of the 336 starting configurations. Of course, each of those starting configurations, he needed 20 nanoseconds of simulation time. So, but looking at a smaller BigJob here with 21 core, 21 or 42 or 36 sub-jobs, you can see that the wait times were quite varying amongst the systems, but more or less all the simulations ran to completion in about the same amount of time. And this is a paper by Shantanu et al. Under review now. Well, this is on the smaller scale of what BigJob can do. By looking at a system the size of Kraken, where its PBS is biased towards larger jobs, you can add more of these sub-jobs, these 1 nanosecond NAMD jobs. You can pack them into a larger container and submit it to Kraken, and Kraken can take that and run with it. And as you can see, the wait times were quite agreeable with them, and all the run times are about the same. And due to this, Tom Bishop was a victim of success at Saga, which he had to request for a supplement because he burned up a lot of his allocation. I'd like to take a quick second to thank the allocation team for pushing his supplement through. He found a pretty amazing science here where I strongly advise people here to look at our video that Nancy will load up later, that the red spots in this animation here, if you look at it, are deformations in the DNA where if in the animation there's going to be red dots that will appear around all the histones here, and that's due to either a kink in the DNA as it goes over a bad part, or not necessarily a bad part, but a unagreeable part of the surface of the histone, or it could be a weak spot in the DNA. Tom found that it happens kind of in interplay of both mechanical properties of the DNA and the shape of the protein itself. And this is for you, Yaakoub.
Right. So a couple of things to add there. These simulations were essentially 126 subjobs, each a 192 core simulation in its own right. These are completely independent NAMD simulations in Tom Bishop's work, and what we're doing with Levy is essentially running something similar, but with loosely coupled simulations. So it's going to be a bit more tricky in terms of data exchange. Another thing that I want to mention is that you will be able to submit the same BigJob to different distributed sites through different submission mechanisms. So while you will be able to submit, say, through Gram to Kraken, you can submit to Condor G to Ranger, and to Unicore to some other machine, perhaps. All of this can take place through the Dare Science Gateway framework, which supports BigJob underneath and provides a very transparent, very easy-to-use interface for domain scientists. This is a Science Gateway framework that supports Ensemble, MD users, and Replica Exchange users. There's quite a few of those users around, so adding a Science Gateway interface to BigJob for them to use is obviously a good idea. We have therefore helped build two gateways, the Dare NGS and the HTHP gateway. The Dare NGS is the next generation sequence analysis gateway, and it is NIH supported. The HTHP is the high performance, high throughput parallel code gateway that runs NAMD and AMBER across obviously multiple distributed resources all at the same time. The Dare infrastructure looks a little bit like this. As is the case with Saga, it is highly layered. The secret sauce is in layers L1 and L2, so that the user interface and the applications and capabilities and services layer, these dictate essentially what workflow you will be using, what actual application you will be using, what arguments to pass, if there is a complex pipeline workflow, if it's an ensemble, if there's communication or not. So where we are now, considering that we started September 15th officially, we have got Saga deployed on XSEDE resources, we have modules to support it, we have a central DB that is hosted on a data query virtual machine. We have since moved from the small machine hosted by the Saga development team. We have deployed BigJob on Ranger. We have tested that. We have scripts to test NAMD and Impact on Ranger and Kraken. We are working on the Science Gateway. It is done. It can't submit quite yet. And we're essentially preparing to run large-scale and production tests, hopefully by the end of next week. And with that, I'll leave you with a few references, and I'll field any questions you might have.
Yaakoub and Matt, thank you very much. That was a very, very interesting presentation. Sounds like you've made quite a lot of progress since last December, so congratulations. I had let's see, I don't see any questions coming in from chat just yet, but I had a few of my own. The Dare gateway for the MD ensembles, is that something that you view as being generally usable, or was it tailored specifically to Levy or some of the other researchers' work?
We want to make them as general as possible. However, there is a bit of customization that goes into them. For example, you have to say which community account you'll be using and things like that. But in the end, what we foresee is that we will provide all the bare bones and sample gateways for particular applications in a virtual machine bundle that users can just run on data query, just make a copy, run on data query, and customize to suit their own needs.
Okay, so you envision using the Quarry VM and kind of providing an image of Dare that people can then customize themselves?
Pretty much.
Yeah. Okay. Yeah. Sounds very good. Let's see. Okay. So there's a question from Yan Lu who asks if there's a demo for the Dare Science Gateway framework or end user interface. Dare.cct.lsu.edu, and we will be, if you go to the Saga website, we will have a link to the gateway that we're hosting on the VM shortly. Okay, so it looks like the last URL that's showing in the reference slide right now, and I think your contact info is also on the web, so if Yan wants to ask a follow-up afterwards. Absolutely. That connection. Ross Walker's got a question. Ross, do you want to type it into chat, or do you want me to unmute everybody so you can express it in your own words? Let me go on to the next question while you decide whether to type or not. We've got about 50 people on, so I'm just worried about the unmute. Oh, okay, unmute. All right, hang on a second.
Presentation mode is now disabled.
Okay, Ross, do you want to go ahead?
Yeah, thanks. It's easier to ask a question than to type it, I think. But yeah. I think it's a nice presentation, and I was very interested in it because we do a lot of replica exchange simulations ourselves. One of the things I'd be interested to know is what's the real advantage of this over the traditional way people do replica exchange? So we use MPI right now and we've happily run like 10,000 core jobs with MPI. I'm just wondering where you see the real advantage of this over just using an MPI approach.
Well, you will have, in our approach, you will have flexible execution at runtime. So if you cannot get 50,000 core job through a single machine, and you are forced to partition it across 3 big machines, you will be able to do this. If you use a flexible framework as opposed to a rigid MPI that needs a straight point-to-point communication.
Sure, but I'm just wondering, do you have any performance numbers for that? Because there's a lot of evidence now that shows replica exchange is much better if you essentially attempt to exchange on every time step. So the more often you attempt to exchange, the better sampling you get. So if you're exchanging on every time step, you've got a large amount of data that you've got to shift, which going between machines might be pretty tough.
So this is for a coupled replica exchange as opposed to completely independent, right?
Well, it has to be coupled to be, otherwise it's just running a bunch of MD simulations.
Right.
I mean, the minimum we have is temperature. So. Right.
So for that, there is a Royal Society paper. It's on the Saga project. I think it's by Ja and his team. Mm-hmm. I'm not sure of the title. I can send you a link. Give me a second to find it. In the meantime, any other questions that I can field?
One question. This is Kent. Isn't the exchange on every time step quite severe, Ross?
Yeah, I mean we do it on about every 10th time step right now, which doesn't hurt too much. Okay. It depends on how many cores you're running on, essentially per replica. But I mean, you can show that it's a diminishing return, but certainly every 10 steps is much better than every 100. Every 5 steps is a little better than every 10, and so on.
Okay, good. Thank you.
I think Kent also had a question about the wait times, the key wait times on the various systems. Were they consistent across systems in your experience?
Yeah.
Sorry, Matt can answer that one.
So the key wait times were more or less consistent. The only key wait times that was quite noticeable was on Lone Star, but as I understand, that's a shared resource between XSEDE and TACC.
So were those for about 100 and say 200 cores? Or I noticed on one of your slides you had 24,000 up there on top. But what size are you usually waiting for? That you'd have Q-step, you'd have waits in the order or less than say 300 minutes?
About 2,000.
Okay, so you're doing 2,000.
Around that, yes.
So 2,000, anything between 2,000 and 25,000 cores on Kraken, right, Matt? Those are the wait times?
Yes. Well, the wait times were about 200 minutes or so at that range.
And Ross, I sent around the Nancy, I think, forwarded to everybody the paper that that I wanted to show you about the replica exchange stuff for diminishing returns issue. Other than that, any other questions?
I was curious. You had said that you've got like 200 MD papers and things. Are there any of those users kind of lined up or said they're interested?
Well, we actually have quite a few lined up. The users, I think, is slide. Some of our users are on. I don't have slide numbers. I'm sorry. Eric Flemington, Tom Keys, Gissendaner, Rankinen. Many people are interested, and hopefully we'll be able to showcase it to a few more people and get them also using it. But from a perspective of a consultant, if more people use the same architecture, it's much easier to support. So I'm hoping that a lot of people will pick this up.
Yeah, very nice.
That's one of the reasons why we're trying to make it into a gateway, that people will be able to use a standardized interface, and hopefully would get less errors when people start their own script. Well, than when people customize their own really contorted Perl script that I have to deal with all the time. Sorry.
Yeah, I think we'll Suresh and I will follow up with you offline, Yaakoub, on the gateway kind of advertising and listing and community account mechanisms and all of that sort of thing. Ralph, sorry, I've got my own background noise here. Ralph Roskis asks also about the trade-offs of using Saga versus something like MyCluster. I'm not sure how familiar you are with MyCluster.
I can't say I'm terribly familiar, but if I understand correctly, MyCluster is not being actively developed.
I think that might be the case. I think actually everyone's on unmute, Ralph, if you want to add anything else to your question.
And it's not deployed on any of the XSEDE resources, at least not as far as I know.
Okay, but I mean, just the general idea that I'm just wondering. I mean, you're probably right. I think it was Ed Walker who started it, and he's no longer at TACC and so on. But I mean, is there some? I mean, one idea here that is not in MyCluster is this idea of running on totally separate machines. But I'm wondering about things like overhead and so on.
Well, the overhead from Saga, I can tell you off the bat, it's minimal, and you can have a look at it at the Saga Demo webpage and see the overhead from the demos that we actually have, and those are very simple, unoptimized, very basic elementary demos. We are not optimizing for the absolute fastest performance when you're launching a job, because that's a very tiny fraction, as in minutes, maybe probably less, almost all the time, compared to a multi-day simulation. So you're not saving a whole lot by making the communication layer, say, C as opposed to Python. That being said,
I guess I'm asking a slightly different question, which is there a new idea in here that wasn't incorporated? Maybe the the packaging is slicker in Saga, but is there a new idea in here for how you do things as opposed to the way MyCluster did it?
Well, it's extensible for one, it's distributed for another, it supports parallel jobs across multiple sites for a third. Other than that, I can safely say I don't know much about MyCluster to be able to draw a finer distinction.
Okay, thanks.
This is Sergio. You mentioned, multi-day runtimes. Is there a facility for, checkpointing, maybe migrating from one machine to another if the original machine where that task was being handled happens to go down?
Yes, there is a distributed coordination system. There is a fault tolerance system. In fact, I actually used it for my master's thesis, and it's all there. We really made it so that it's difficult to kill entirely. That sometimes causes a problem, but in all likelihood, it's always a good thing.
That what is difficult to kill entirely?
So it's essentially, when I launched it on Ranger, on Queen Bee, and Abe. Yeah. And I had 128 ensemble members, and each was a reservoir simulation. And I ran with a global synchronization point for many time steps. Okay. And so if I wanted to terminate, I have to go in and terminate it on all three machines, because whatever happens, if I kill it on one machine, it would round robin and distribute to the other two. So you'd always have to kill it in all three places. We have since then added a master kill switch.
Okay, so that's like if you want to disable this feature.
Absolutely. So you can.
It seems wise not to disable it, right? Because you never know when one of the machines could go down, or at least that job could die on that machine.
Yes, but for example, if you discover that you have a problem with one of the input parameter files and you need to change it, then you need to shut down the thing.
Okay. So, yeah, it's good to have the option to do it, but Yeah. Okay.
Yeah.
So, but on the positive side, it does have this provision for surviving part of the system going down.
The only thing it cannot survive is a complete network failure. If you can't, for example, talk to the service that tells it where to get jobs from, then obviously it can't get the jobs that it needs to.
So is there like a central, pulse node or command node that everybody has to stay in touch with?
Yes, it's the advert service node, and that's why we're putting it as a virtual machine on data query, so that users can roll their own and start duplicates if they want to, and they can swap one with another, and so on. Essentially, is there an option for avoiding the single point of failure by having, say, an option for even moving the advert service around, or having like a backup advert service that can kick in or something like that? So
like if, the connection in Indiana goes down.
Right. Because it's a virtual machine, if it goes down, you can bring it back up quite easily.
And that is kind of in the software, this
yes.
feature? Oh, okay. So there's not really a single point of failure in the form of the advert service.
Well, if, for example, data query goes down and all of your simulations are hard-coded to work with data query, then, but to be fair, if data query goes down, which is incredibly unlikely, you have more serious, people on XSEDE have more serious problems.
Yeah, okay. Thank you.
Thanks. I think we had one more comment that Shantanu would like to make to something Ralph asked about.
Sure. Nancy, can you hear me?
Yep.
Great. Ralph, just wanted to respond to your earlier question distinguishing MyCluster from Saga. MyCluster was a system-level tool almost deployed on a given system, whereas Saga is as you might remember, a programming abstraction. And most importantly, what that means is it's scriptable, extensible, customizable. And I think that's the fundamental difference. And obviously with Saga being deployed as an access layer on XSEDE, what you now have is a software component which, as a consequence of being deployed already, works seamlessly on any of the other XSEDE machines. So subtle differences, but I think very important differences, and hopefully users have voted with their feet in at least two examples you saw.
Okay, I got it.
Okay, thank you very much. I think we're just a bit over time. I think that all the questions that are submitted in chat were addressed. Yes. I want to thank our large number of attendees. We had close to 50 people join, and some of those connections were representing large groups of people in a single room. So we had quite a lot, and I especially want to thank our three speakers who agreed to be guinea pigs for this and worked back and forth with me quite a bit to kind of iron out all the the technical details, and I think did a fine job on their talk. So thank you very much, Yaakoub, Matt, Darren. Thank you very much, and hopefully we'll see everyone next month for our second one of these. Thanks, everyone.
Thank you.